Okay, so that takes care of one of my eigenvalues and eigenspaces, because right here, this gives me, since there's only one free variable affiliated with this particular lambda, I know that the span of this vector will be the eigenspace affiliated to this particular lambda value, okay? What I might be interested in is, how do I find the other one? Well, you could do the same basic calculations, but in complex arithmetic, there's a little bit of a shortcut that we can take. So in order for me to introduce that, I need to define a couple of terms, just to make sure. Okay, I'm going to let z be a plus bi. This is a complex number. We can define the conjugate of z is z bar, which is a minus bi. Okay. The real part of z, we say re of z is just a, and the imaginary part of z, we denote im of z as equal to b. Okay. Most of you are taking complex analysis next semester, and you'll be very familiar with this by the end of, by probably week 2. So I can define x. So these are just complex numbers of a single complex number. I can also create vectors of complex numbers that I alluded to at the beginning of class. So if I let x be in Cn, I can think of x as having n entries. Each of them is a complex number. So if once I have a vector, I can define the conjugate of the vector is just the vector of conjugates, z1 bar, z2 bar, all the way down to zn bar. Okay. Similarly, I can take the real part of a vector as the vector of real parts. And the imaginary part of a vector as the imaginary part of each of my entries. Okay. So properties of conjugates from complex algebra do carry over to matrix vector operations. Okay. And there's a very helpful proposition that we have here. So I'm going to suppose if A is a real valued n by n matrix. Okay. Now I've used this notation all throughout the class, but here's where it's actually important to pay attention to it. Normally you just focused up here to say what the dimensions of the matrix were, but here, what space I'm picking the entries from matters. Okay. So this statement is not true if A is complex valued. This has to be A is real valued matrix. All right. So A is a real valued n by n matrix with an eigenvalue lambda in the complex plane with eigenvector x in Cn. Then lambda bar is an eigenvalue with eigenvector x bar. Okay. So here's, all right, so if I'm looking at ax is equal to lambda x, I'm going to take the complex conjugate of both sides of the equation. One of the things you can do with complex conjugates is split them across multiplication. And here's the kicker. Since A is real valued, the complex conjugate of A is just itself. And that's what all we needed to show. This shows that lambda bar is an eigenvalue and the eigenvector affiliated with it is x bar. Okay. So really what this says is that complex eigenvalues come in conjugate pairs. Okay. Complex eigenvalues and eigenvectors come in conjugate pairs. But this fact also kind of follows from the fundamental theorem of arithmetic, right? So we think of lambda as the root of a characteristic polynomial. Our understanding of roots of polynomials says that roots of polynomials come in conjugate pairs if I have real value coefficients, right? So this shouldn't be that surprising to us. So for our particular example that we had, with our A being, 0.5, 0.75, negative 0.6, and 1.1, we had lambda 1 is 0.8 minus 0.6i with a vector of negative 2 minus 4i and 5. Okay. We can easily find the other by taking the conjugate of that. So if I take the conjugate of lambda 1, I get lambda 2, which is 0.8 plus 0.6i. And I can get the conjugate of v as the associated eigenvector. So to take the conjugate of v, I just flip this to be negative 2 plus 4i. And since 5 is a real number, the imaginary part is going to stay 0. That's kind of nice. If you know that you have a complex eigenvalue, and you find the basis of the eigenspace for that particular eigenvalue, you automatically have also found the eigenspace affiliated with lambda bar, with the conjugate of lambda.